Hi everyone. So today we're going to be talking about z-score and how it relates to standard deviation. This is the last unit or section of our unit on univariate data, and so it's a culminating lesson. So first, let's review what the standard deviation was. In the last lesson, we learned that the standard deviation is the typical distance from the mean. Now what the z-score is it is a number that tells us how many standard deviations a data value lies above or below the mean. So it kind of gives a data point a little bit of extra meaning so that I know exactly where it's sitting in the data. So if you have a positive z-score, that would mean that your data value lies above the mean. So that data lies above the mean. A negative z-score is the opposite. It tells you that a data value is going to lie below the mean. And a z-score of 0 means that the data value is equal to that mean. So let's look at an example. We have a data set that has a mean of 15 and a standard deviation of 2. I want to find the z-score of the following data values. So let's consider an illustration. I'm going to draw a number line. And I'm going to put 15 at the middle, since that is my mean. So I know here at 15, my z-score is equal to 0. Now let's start going out on my number line by units of 2, since that is the standard deviation. So if I go out 16, 17, 18, 19, 21, 23, and I'm running out of space. Let's go the other direction. 14, 13, 12, 11, 10, 9, 8, 7. All right, so where I've actually given myself some numbers, that's going to tell me where my z-score is going to increase by one value. So with a standard deviation of 2, I've increased 2, so my z-score here at 17 will be 1. If I go out another standard deviation, 2 more units to 19, my z-score will be equal to 2. Another one at 21, my z-score is 3. And at 23, my z-score is 4, and so forth. Now in the opposite direction, if I were to move from 15 and I were going to go out to 13 in the negative direction, 13 would give me a z-score of -1. And 11 is a z-score of -2. 2 more back, z-score of -3 at 9. And a z-score of -4 at 7. And it doesn't stop there. I can keep going on and on and on. So when I'm asked to find the z-score of the following data points, some of these I'm going to be able to pluck right off of my number line. So I can see on 21 the z-score is 3. 11, z-score is -2. 19 is 2. 18 is not on my number line. 4 is not on my number line. 25, I didn't go out that far. 7, I can see, is -4. 15 is 0. 30 is not on my number line. And 13 is -1. So you can see how simple those were because I can pluck them right off my number line. But what about some of these other ones that fall off of my number line, or I have some even numbers here, so that might be a little more complicated. So 18 is the first one that I'm noticing. So I can see 18 is right here, and it is exactly halfway in between 17 with a z-score of 1 and 19 with a z-score of 2. So if I take the average between 1 and 2, I can see my z-score is going to be 1.5. 4 is way off of my number line, so I'm going to even come back for that one. 25 is just one more unit out, so I can probably squeeze that in and see it's going to have a z-score of 5, one more unit out. Leaving me with 30, which is again, 4 and 30 are way off of my number line, and they're both odd or even numbers. So I'm probably not going to have an integer being my z-score. So what that leaves me with is a need for kind of a formula, a way that I can simply find what the z-score is. Well, let's think about what we're actually analyzing here, how I would find, let's just use 19. I'm looking at how many standard deviations 19 lies from the mean. So there's a need to calculate this distance right here. So that distance would be 19 minus 15, or the data value minus the mean. And then I want to know how many chunks of 2 I have within this distance. And I'm looking at chunks of 2 because that's the standard deviation. So once I calculated the distance, which is 4, I would then divide that by that standard deviation of 2 to see the z-score is indeed 2. So I've got my distance, x minus x bar. Then if I divide by the standard deviation, s, like I did right here, that'll give me a nice formula for the z-score. So in summary, if I'm looking for the z-score, all I need to know is the data point, the mean, and the standard deviation. And let's try it with 4. So I want to know the z-score for 4. So I'm going to say data point of 4 minus the mean divided by the standard deviation. Well, 4 minus 15 is negative 11. And if I divide that by 2, I get negative 5.5. So there's the z-score for 4. For 30, we can do the same thing. Take my data point of 30 minus 15 and divide that by 2. I end up with 15 over 2, and 15 divided by 2 is going to be 7.5. So my z-score for 30 is 7.5. Okay, so now let's recall a little bit of notation and some formula with those, not notation. So remember, when I have a mean of a sample, I'm going to use x bar, and that's usually what I am able to find. When I can get a full population mean, I'm going to use mu. Standard deviation of a sample is little s, but if I can get the full population, that standard deviation is here. So z-score now, if I were looking at that formula that we hopefully discovered in the last slide, z-score of a sample is going to be x minus x bar all over s, whereas z-score of a full population is going to be that data point is still x minus my mu over my standard deviation. All right, so here's an example for you to do. So I encourage you to pause the video and work on this chart. It says let the mean be 80 and the standard deviation be 10. Find the following z-scores for the listed scores in the table below. So it looks like this is probably maybe scores on an assessment for a class. So you're going to go through and find the z-scores for every score, and then what I'd like you to do is come back and check your work. So pause the video now, and when you unpause it, the answers are going to come up. Okay, so now that you've had a moment to go through all of the scores and calculate the z-score, you can come and check your answers. Notice that any score above an 80 has a positive z-score, and any score below an 80 has a negative z-score. And that standard deviation is actually quite large, so you can see we've got some decimals here, like 3/10 and negative 8/10. All right, let's take a look at this one. It says, a patient recently diagnosed with Alzheimer's disease takes a cognitive abilities test. The patient scores a 45 on the test. The data has a mean of 52 and a standard deviation of 5. What z-score would the patient be given? So let's take a note of all of the things we need. So to find z-score, I definitely need the data point I'm working with. That's this 45 right here. I need the mean, that's the 52. And I need the standard deviation of 5. So you can see I have everything I need to calculate the z-score that would be used to describe the patient's score on this cognitive abilities test. So my z-score is going to be the data value 45 minus the mean, which is 52, all divided by 5. So I end up with negative 7 over 5, which is negative 1.4. So if I'm a doctor and I'm analyzing these results, and I see that the patient's cognitive abilities test lied almost 1.5 standard deviations below the mean, I could then make a quick observation that this person's disease has progressed a little further than the average, which was a 52. Let's consider this next problem. A student in AP Statistics gets a graded paper back with the following data written at the top of their paper. What is the student's score? I feel like AP Stats teachers and just Stats teachers in general love to do this. So you can see they have the mean of an 82, a standard deviation of 2, and they just said, hey, you are a 1.5. So immediately I'm happy because I know my score, if I'm the student, is above the mean, which is exciting. But if I'm going to calculate this, I'm going to go back to my formula, if you choose to do it this way. And you're going to say, all right, well, my z-score is 1.5. I don't know my actual score, but I know the mean is 82, divided by the standard deviation, which is 2. And now I have a simple linear equation to solve. So first, I'm going to multiply by 2 on both sides, giving me 3 equals x minus 82. Then I need to add 82 on both sides. And I can see my score on this test was an 85. Very exciting. So some people really like this formula. Other people like to logically think through it. And that's okay. If the numbers aren't too messy, you can definitely logic your way through this one. You can consider a number line, put your mean at 82. 1 standard deviation away, a z-score of 1 would put you at 84. I'm just adding 2. So here at 84, my z-score is 1. Go out another standard deviation and add 2 more. That puts me at 86, and my z-score there would be 2. Well, my z-score was 1.5, which is right in the middle. So that means I got an 85%. That's my score. All right, our final activity for this lesson is to open up a Fathom file called Motor Vehicles, and I want you to analyze the data, which now includes standard deviation. Then I want you to calculate the z-score for the following states listed. So let's review really quickly before you get started. What does it mean to analyze the data? Well, to analyze the data, the first thing, you gotta give me the shape of the data. So looking at a dot plot is a really easy way to take a look at that. But you can look at other displays as well. You need to give me your 5-number summary, your mean, and the standard deviation. Next, you've got to analyze outliers. You need to show all of your work both for upper outliers and for lower outliers using that 1.5 times IQR. So you'll analyze, find your upper cut, lower cut, and then list any of your outliers. So that's how you're analyzing the data. And then the last step that I want you guys to do, the new step, which isn't part of analyzing the data, this is just an extra question, is to calculate the z-score for the following states. And that's it for univariate data.